Today we're going to be learning Unit 2, Lesson 3, Trigonometric Identities, Part 3. Part 2. So learning goals for today, after this lesson, you will be able to understand and prove trigonometric identities featuring minus theta. Next, understand and prove trigonometric identities featuring theta plus half pi multiplied by a integer number k. Third, use equivalent trigonometric expressions to solve problems. Okay, so first of all, let's have a look at the trigonometric identities featuring minus theta. Okay, so basically, if let's consider the cases where theta is not on the x and y axis first. So if theta is not on the x and y axis, there are four cases, right? Theta could be in the first quadrant, or the second, or the third, or the fourth. So let's have a look at if theta is in the first quadrant. That means let's have a look at this graph first. Okay, for example, if theta is here, then we know that minus theta must be in the fourth quadrant, right? And the angle here is exactly the same with angle here, right? Because we have already reviewed that for a positive angle, we turn the angle anti-clockwise, right? And for a negative angle, we just turn the angle clockwise. So if theta is here, minus theta must be in the fourth quadrant, right? And if we have a point on the terminal side of theta with coordinates x and y, and the distance between this point and the origin point O is r, and we know that in the angle minus theta, the corresponding point P prime must has a coordinates x and minus y, right? Because these two triangles here are congruent, right? So the x coordinate of P prime is the same with P, which is x. And the distance between P prime and x-axis is the same with the y coordinate of P, which is y. But because P prime is in the fourth quadrant, the y coordinate must be negative, right? So the y coordinate of P prime must be minus y. Understand? Okay, so now let's look at the other cases. In the second quadrant, third quadrant, and fourth quadrant, similar thing will happen. If P is xy, if P with coordinates xy in the terminal side of theta, then the corresponding B prime must have a coordinates x minus y in the terminal side of minus theta, right? Okay, so now if we want to calculate the trigonometric ratios for minus theta, for example, sine minus theta, according to the definition, it is defined as the y coordinate over the distance between this point and the origin point, right? The y coordinate of this point P prime is minus y. So sine minus theta is minus y over r. Understand? Minus y over r. So now let's consider y over r. Y over r is actually sine theta, right? Because on the terminal side of theta, P has coordinates x and y. So according to the definition of sine theta is just the y coordinate over the distance r, right? So in this way, we have proved that sine minus theta is actually minus sine theta. Understand? Okay, so use similar way, we can also prove that cosine theta equals x over r, which is actually cosine theta, right? And similarly, tangent minus theta is minus y over x, which is minus sine theta, right? Okay, so these are the identities for the primary ratios. For the secondary ratios, we can also use similar way to prove them. For example, cosecant minus theta equals minus cosecant theta. Secant minus theta equals secant theta. And cotangent minus theta equals minus cotangent theta, right? For your convenience, you can just remember the first three ratios and use the reciprocal identity to deduct the identities for the other three ratios, right? For example, because cosecant is the reciprocal of sine, so it must have similar properties with sine, right? And secant is the reciprocal of cosine, so it must have similar properties with cosine. And similar thing will happen for cotangent and tangent. Do you understand? Okay, so let's have a look at the second case. If the angle theta lies on the x or y axis, what will happen? Okay, first of all, theta can be in the positive side of x-axis, right? And it can also be on the positive y-axis or negative x-axis or negative y-axis, right? So in this way, we can also prove that sine minus theta equals minus sine theta. For example, let's have a look at the first case. If theta is in the positive side of x-axis, this minus theta must also be the same with the terminal side of minus theta must be the same with theta, right? So in this case, sine minus theta is simply 0, and sine theta is also 0. So this expression holds true for this case, right? And for this case, cosine minus theta is 1, and cosine theta is also 1. So this expression also holds true for cosine theta. And for tangent theta and tangent minus theta, both of them are undefined, or in other words, positive infinity, right? So this expression also holds true for tangent theta. And for the other three trigonometric ratios, according to the reciprocal identities, these three expressions are also true. Okay, and if you consider the other three cases, all of the properties here can be proved, right? So in a summary, we have sine minus theta equals minus sine theta. Cosine minus theta equals cosine theta. Tangent minus theta equals minus tangent theta. That means sine theta is actually an odd function, right? And cosine theta is an even function. And tangent theta is an odd function, right? And cosecant theta, because it is a reciprocal of sine theta, so it is also an odd function. And secant theta, because it is a reciprocal of cosine function, so this function is an even function. And cotangent theta is a reciprocal of tangent theta, so this is an odd function. Understand? So this is the first set of properties we have learned for today. You can spend some time writing these properties down onto your notebook, okay? I'll give you 3 minutes. Have a look at them. All right, have you finished? Let's have a look at the second set of trigonometric identities we're going to learn today. So the second set of trigonometric identities is the identities featuring theta plus half pi multiplied by an integer number. So k here is any integer number, such as -3, -2, -1, 0, 1, 2, 3, etc. So first, let's discuss the cases where k equals 1 or 2. The other cases can be inferred from these two cases. Okay, so first let's have a look at when k is 1. So when k is 1, first let's consider if theta is not on the x-axis or y-axis. For example, theta could be in the first quadrant, second or third, or the fourth quadrant, right? So first of all, let's have a look at if theta is in the first quadrant. Let's focus on this case first. So if theta is in the first quadrant, theta plus half pi should be in the second quadrant, right? That means we can simply turn the terminal side of theta counterclockwise to another half pi, which means the theta plus half pi must lie in the second quadrant, right? So if we have a point P, X, Y in the terminal side of theta, after you have turned the terminal side for half pi counterclockwise, the corresponding P prime, P is actually come to a position denoted by P prime, right? And corresponding P prime has the coordinates -y and x, right? And if you want to find the trigonometric ratios of theta plus half pi, we can then use the definition to calculate them, right? So for example, if you want to calculate sine theta plus half pi, because we have a point here, according to the definition, sine theta plus half pi is a y coordinate, which is x, right, over the distance, which is r. And note that in the original angle theta, x over r happens to be the cosine theta, right? Because by definition, cosine theta is x coordinate x over distance r, right? So in this way, we can prove that sine theta plus half pi equals cosine theta. Understand? And same thing will also happen if theta is in the either in the second or third or fourth quadrant. If you have a point P, X, Y, after we have turned this angle to another half pi counterclockwise, P will come to a position to P prime with coordinates -y, x. Same thing will happen in the first, second, third, and fourth quadrant, right? So no matter theta in which quadrant, we all have the relationship sine theta plus half pi equals cosine theta. You understand? Okay. And now let's have a look at cosine theta plus half pi. Using the same method, according to the definition, cosine theta plus half pi is the x coordinate of theta plus half pi, which is, you can use this point here, right? Which is -y over r. And note that y over r is actually, according to the definition, is sine theta, is in the original angle, right? Because for the point P here, y is y coordinate. Y coordinate over r is defined as sine theta. So in this way, we can prove that cosine theta plus half pi equals minus sine theta. Understand? Okay, so following the same method, you can also prove that tangent theta plus half pi equals x over minus y, right? Let's consider the theta plus half pi here. According to the definition, tangent theta plus half pi equals the y coordinate over x coordinate. Y coordinate is x, right? Because we are now considering p prime. The y coordinate is x, and x coordinate is minus y, right? And in the original angle theta, x over y is actually defined as cotangent theta, right? Okay, so in this way, we have proved that tangent theta plus half pi equals minus cotangent theta, right? Okay, so these are for the primary trigonometric ratios. For the secondary trigonometric ratios, we can easily use the reciprocal identities to prove that cosecant theta plus half pi equals secant theta, because cosecant is just the reciprocal of sine, right? So both of them have similar properties. And secant theta plus half pi equals minus cosecant theta. Whereas cotangent theta plus half pi equals minus tangent theta. Understand? Any questions? Okay, so these are the cases that if theta is not on either x and y axis. So in order to prove this is a trigonometric identity, we also need to prove if theta is on x and or y axis. These identities will still hold. Only in this way, these are applicable for any theta, right? So for example, if theta is on the positive axis, then we know that theta plus half pi must lie in the positive y-axis, right? Because theta plus half pi is simply turning theta counterclockwise for another half pi, right? Okay, so let's consider this case first. In this case, if p has coordinate x 0, then after turning the half pi counterclockwise, p will come to a position p prime with coordinates 0, x. Understand? So now sine theta plus half pi is actually 1, right? So sine theta plus half pi is 1. And note here, cosine theta is also 1, right? So this expression holds true for theta in positive x-axis. And you can also check if theta is in positive y-axis or negative x-axis or negative y-axis. This expression here also holds true for the other cases, right? So in this way, we have proved that for any theta in the domain, we always have sine theta plus half pi equals cosine theta. You understand? And similarly, we can use the same method to check that for any theta that lies in x-axis or y-axis, we can also have cosine theta plus half pi equals minus sine theta. And tangent theta plus half pi equals minus cotangent theta. So that means for any theta in the domain, these expressions hold true. Therefore, these can be called trigonometric identities, right? Because they are true for all theta in the domain. Understand? Okay, so let's make a summary. Okay, for trigonometric identities featuring theta plus half pi times k, when k is 1, that means half pi times k is half pi, right? We have the following trigonometric identities. First, sine theta plus half pi equals cosine theta. then cosine theta plus half pi is minus sine theta. And tangent theta plus half pi is cotangent theta, right? Okay, so for your convenience, it's better for you to remember these three trigonometric ratios first, and then the other three can be easily deducted from the reciprocal identities, right? So for example, cosecant is just the reciprocal of sine. So these two have similar behavior. And secant is just reciprocal of cosine. So these two have similar behavior. And cotangent is just the reciprocal of tangent, right? So these two ratios have similar behavior. Okay? Any questions? Okay, so please spend some time writing these properties down onto your notebook. We're going to use this to solve some problems later, okay? Okay, have you finished? All right, so let's consider the case where k is 2. So as you can see here, when k is 2, theta plus half pi times k becomes theta plus pi, right? So again, first let's have a look at cases where theta is not on the x nor the y-axis. So for example, theta could lie in the first, second, third, and fourth quadrant, right? So let's have a look at if theta is in the fourth quadrant. Suppose P is a point on the terminal side of theta with coordinates x and y. So theta plus pi must be in the third quadrant, right? Because theta plus pi is simply turn theta counterclockwise for another pi, which means the terminal side of these two angles must be in the same line, right? Remember that this is pi. So the original point P with coordinates x and y here will come to a new position P prime with coordinates minus x minus y, right? Because as you can see here easily, x and y are both positive, right? And after you turn them to another pi counterclockwise, both of the coordinates are now negative, right? But the absolute values of x and y should be the same. So P prime has the coordinates minus x and minus y, right? And same thing will happen if theta is in the second quadrant or third quadrant or the fourth quadrant, right? For all of the other quadrants, Pxy will come to a new position P prime minus x minus y. Understand? Okay, so in this case, if we want to calculate or evaluate sine theta plus pi, we can easily see that by definition, the sine ratio of this angle here is y coordinates over distance r, right? And y coordinates, let's use P prime, is actually minus y, right? For all of the quadrants here, all of the cases here, the y coordinates are all minus y. So minus y over r. And also note that y over r in the original angle theta is actually defined as sine theta, right? So in this way, we have proved that sine theta plus pi is actually minus sine theta, right? Any questions? And similarly, cosine theta plus pi is defined as the x coordinate, which is x coordinate of P prime minus x over r. And also note that x over r in the original angle theta is defined as cosine theta, right? So cosine theta plus pi is actually minus cosine theta. And similarly, tangent theta plus pi is y coordinate minus y over x coordinate minus x, which is tangent theta. Understand? Okay, so these are for the primary trigonometric ratios. For the other ratios, again, we can use the reciprocal property to deduct the expressions for cosecant, secant, and cotangent. For example, cosecant theta plus pi is minus cosecant theta. Secant theta plus pi is minus secant theta. And cotangent theta plus pi is cotangent theta. Understand? Okay, again, let's consider if theta lies in the x-axis or y-axis, what will happen? So similar to 1k is 1. For example, let's consider the first case here. If theta is on the positive side of x-axis, then theta plus pi must be to the opposite, which is in the negative x-axis, right? So if you have a point P in the terminal side of theta with coordinates x and 0, and after you turn this angle for another pi counterclockwise, P will come to a position to P prime with coordinates minus x 0, right? Okay, so if you want to evaluate sine theta plus pi, according to the definition, we need to use the y coordinate 0 over r. So the left side is 0, right? Right side is also 0 over r, which is 0, right? So this relationship will also hold true for theta in positive x-axis, right? And same thing will happen if you consider that theta is in the positive y-axis, negative x-axis, or negative y-axis. Understand? Okay, so in this way, we have proved that for any theta in the domain, we have this relationship, which is sine theta plus pi equals minus sine theta. And use similar method, we can also prove that cosine theta plus pi equals minus cosine theta, and tangent theta plus pi equals tangent theta, right? Okay, so this is for the primary ratios. For secondary ratios, again, use the reciprocal property. We can also prove that cosecant theta plus pi equals minus cosecant theta, and secant plus theta plus pi equals minus secant theta, and cotangent theta plus pi equals cotangent theta. Understand? Okay, then I'll give you some time to write these properties down onto your notebook. Okay, these are the cases 1, k equals 2. Okay, have you finished? All right, so let's consider the cases where k equals 3. So as I said, when k is 3, these cases can be inferred to by considering k is 1 or 2. So for example, sine theta plus 3 pi over 2. So when k is 3, this term here becomes 3 pi over 2, right? Sine theta plus 3 pi over 2 can be rewritten as sine first theta plus half pi, right? And then plus another pi. So half pi plus pi is actually 3 pi over 2. And we have already know that sine alpha plus pi equals minus sine alpha, right? We have already proved this. So if you consider this angle here is alpha, that means sine alpha plus pi, which is minus sine alpha, right? And we have also proved that sine alpha, this time we use theta, sine theta plus half pi equals cosine minus cosine theta, right? So here, sine theta plus half pi equals minus cosine theta. Sorry, made a mistake here. Sine theta plus half pi equals cosine theta, not minus cosine theta, right? And here sine theta plus half pi equals cosine theta. So the final result is cosine theta. So in this way, we have proved that sine theta plus 3 pi over 2 is actually minus cosine theta, right? So similarly, if you want to evaluate cosine theta plus 3 pi over 2, note that we have proved that cosine alpha plus pi equals minus cosine theta, cosine alpha, right? So cosine theta plus 3 pi over 2 can be rewritten as cosine first, theta plus half pi, and then plus another pi, right? So this is our alpha. So cosine alpha plus pi is minus cosine alpha, right? This is our alpha here. And we also proved that, we have already proved that cosine theta plus half pi equals minus sine theta, right? So we use this formula and input the result here. This is actually minus minus will give you positive, right? So positive sine theta. So in this way, we have proved that cosine theta plus 3 pi over 2 is sine theta. Okay, so now let's consider tangent theta 3 pi over 2. So first, we have proved that tangent theta plus pi is actually tangent theta, tangent alpha, right? Tangent alpha plus pi is tangent alpha. So suppose this is all alpha. Tangent alpha plus pi is actually tangent alpha here, right? And we also proved that tangent theta plus half pi equals minus cotangent theta, right? So here tangent theta plus half pi equals minus cotangent theta. So in this way, we have proved that tangent theta plus 3 pi over 2 equals minus cotangent theta, right? So these are for the primary ratios. For second ratios on the right, again, use the reciprocal properties. You can easily see that cosecant has the same property with sine, and secant has the same behavior with cosine, and cotangent has the same behavior with tangent. Understand? Okay, so I'll give you some time to read through this, okay? Any questions, you can let me know. Okay, any questions? No? All right, now let's consider if k is 4. If k is 4, theta plus half pi times k becomes theta plus 2 pi, right? Theta plus 2 pi is easy to calculate because theta plus 2 pi is actually a new angle that has the same terminal side with theta, right? For example, if theta is here, theta plus 2 pi is simply turn theta counterclockwise to another 2 pi, right? Note that 2 pi is actually 360, right? So after you turn this angle for another 360 counterclockwise, actually theta plus 2 pi has the same terminal side with theta. So if you find a point P on theta, point P must be on theta plus 2 pi as well, right? So if two angles have the same terminal side, they have the same trigonometric ratios, right? So we can simply see that sine theta plus 2 pi is actually sine theta. Cosine theta plus 2 pi is actually cosine theta. And tangent theta plus 2 pi is tangent theta, right? And same property applies to the second trigonometric ratios as well. Cosecant, sorry, there's a typo. Cosecant theta plus 2 pi is actually secant theta, and secant theta plus 2 pi is cosecant. Sorry, I have to make the correction here. Sorry about the typo here. Secant theta plus 2 pi is actually secant theta, right? And cotangent theta plus 2 pi equals cotangent theta, right? Okay, so for k equals 5, 6, 7, or -3, -2, -1. Similar results can also be inferred from the properties we have learned so far, right? For example, prove that sine theta plus 25 pi over 2 is cosine theta. How do you prove this? By using the trigonometric identities we just learned. Okay, I'll give you 2 minutes to think about this, okay? Okay, let's have a look at how do we prove this. We can prove it in this way. So note here the left side equals sine theta plus 25 theta over 2, right? And note here, we can rewrite angle here to theta plus half pi, right? And then plus another 12 pi, right? Because half pi plus 12 pi is 25 pi over 2, right? So this is actually theta plus half pi and then plus 6 pi times 2, right? Sorry, not 6 pi. 2 pi multiplied by 6, right? 2 pi multiplied by 6 means 360 degrees, right? So suppose this is your theta plus half pi. By turning 2 pi, it will come here, and another 2 pi come here, another 2 pi come here, another 2 pi comes here, another 2 pi comes here, right? So repeat these actions for 6 times. That means 2 pi multiplied by 6, right? So this new angle here has the same terminal side with the angle here, right? So we only consider this angle. That should be sufficient. So the sine ratio equals sine theta plus half pi, right? Because both of the two angles have the same terminal side, so their sine ratio should be the same, right? Okay, so we have already know that sine theta plus half pi equals cosine theta, right? Which is the right side. So in this way, we have proved this is actually a identity, right? Okay, any questions? Okay, so this means 1k is 5, 6, 7, or -3, -2, -1, or other integers. We can also evaluate the trigonometric ratios using the identities we have just learned, right? So for your convenience, I think you only need to remember that 1k is 1 and 1k is 2, right? The other cases can be easily inferred from the properties we have learned. 1k is 1 or 2. Okay, another example proves that theta minus half pi equals minus cosine theta. This means 1k is -1, right? I'll give you 2 minutes to think about this. Okay, have we finished? Actually, there are two routes you can prove this identity. So first, let's have a look at the first method. So note that the left side is sine theta minus 2 pi, right? We can rewrite this to sine theta minus 2 pi plus 2 pi, right? Because, for example, if this is your theta minus 2 pi, by adding a 2 pi, it is equivalent to turn this angle counterclockwise to another 2 pi, right? So the new angle has the same terminal side with the original angle. So both of the angles should have the same ratios, right? Okay, so this is actually theta sine theta plus 3 pi over 2, right? And we have already proved that in the previous slide. So sine theta plus 3 pi over 2 is actually sine theta plus half pi and then plus another pi, right? Okay, so sine angle plus pi actually equals sine minus sine this angle, right? And then sine theta plus half pi equals cosine theta, right? We have proved this actually. So minus sine theta plus half pi is actually minus cosine theta, which is right side, right? Okay, so this is the first method. And there is another method. Let's call this method 2. So note here, left side equals sine theta minus half pi, right? Which is rewritten as sine minus half pi minus theta, right? Okay, so we have already known that sine minus alpha equals minus sine alpha, right? So here, this is minus sine half pi minus theta, right? And this is actually minus cosine theta by using the cofunction property, right? Cofunction property states that sine half pi minus theta equals cosine theta, right? So this is actually cosine theta here. So the whole expression equals minus cosine theta, which is the right side. Understand? So you can choose either method you prefer. Okay, so you can also check the proof in this slide. All right, so let's do a practice. Prove that cosine theta minus pi equals minus cosine theta. Okay, I'll give you 2 minutes to think about this. Okay, have you finished? Okay, we can start from the left side, right? Left side equals cosine theta minus pi, which is cosine theta minus pi. We can add another 2 pi, right? As we have proved, if you add 2 pi times a integer number here, 2 pi times k is the integer number, right? The trigonometric ratios should be the same with the previous one. So cosine theta minus pi equals cosine minus pi plus 2 pi. And this is actually cosine theta plus pi, right? And we have proved that cosine theta pi is actually cosine theta, right? So as you can see here, when k is 5, 6, or 7, or minus 3, minus 2, minus 1, any other numbers, any other integers, these can all be inferred from the properties we have learned so far, which is the cases when k is 1 or k is 2, right? Okay. All right. So let's make a summary. Actually, there is a shortcut to write the equivalent expression involving positive or negative theta plus half pi times a integer number. The shortcut states that suppose we have a trigonometric ratio named 1 and the angle is positive or negative theta plus half pi times k. This is actually equal to positive or negative. We have a positive or negative sign here. This sign is to be determined, right? And then followed by a trigonometric ratio named 2, and the angle is theta. So there are two things we need to determine. First, the name of the trigonometric ratio 2. Second, the sign in front of the new trigonometric ratio. So first, let's have a look at how do we determine the trigonometric ratio 2 here. So trigonometric ratio named 2 is determined using the following method. If k is an even number, trigonometric ratio number 2 is the same with trigonometric ratio named 1. And if k is an odd number, trigonometric ratio named 2 is a co-function of trigonometric ratio named 1. Okay, that means in this case, when k is an odd number, sine becomes cosine, cosine becomes sine, tangent becomes cotangent, cotangent becomes tangent, cosecant becomes secant, and secant becomes a cosecant becomes secant, and secant becomes cosecant. Understand? And to determine the sign, positive or negative, at this position here, we can use the following method. Assuming theta is an acute angle, which is between 0 and half pi, find which quadrant the angle positive or negative theta plus half pi times k is in. And then you can use the cast rule to determine the sign of trigonometric ratio named 1 in that quadrant. Then use this sign as the sign in this position here. Okay. Okay. Have a look at this. Please take a snapshot or write them down into your notebook, and we'll use this rule, we'll use this shortcut to solve some problems in the following lecture slides. Okay. Okay, have you finished? Okay, let's do some exercises. For example, use the shortcut method to write the equivalent expression. A, sine 33 pi over 2 minus x. B, cosine x plus 55 pi over 2. C, tangent x plus 15 pi. Okay, I'll give you 3 minutes to think about these questions. Okay, have you finished? All right, to use the shortcut method first, let's have a look at the first question. To use the shortcut method, we rewrite the expression here in the standard form, right? Standard form states that minus x or positive x, right? Plus half pi times a integer number. So the integer number is 33, right? And the shortcut method states that if you have negative or positive x here plus a half pi times an integer, this can be rewritten as, first of all, positive or negative, right? And then followed by a new trigonometric ratio name, which is determined by looking at the number here. If the number here is an odd number, you should change the function here to the co-function, right? So sine is changed to cosine x here, right? All right, next we need to determine the sign is negative or positive. This can be determined by assuming x is acute angle. Okay, so minus x plus half pi times 33 is actually minus x plus 32 pi over 3 plus pi over 2, right? And this is actually minus x plus half pi plus 16 pi, right? 16 pi is actually 2 pi multiplied by 8, which means the whole angle here should have the same terminal side with minus x plus half pi, right? So we only need to consider which quadrant this angle is in, right? So assume x is acute angle. So x is a acute angle. Half pi is here, right? So this is half pi. And minus x, x is acute angle. So the new angle should be here. This is minus x plus half pi, right? It must be in the first quadrant. In the first quadrant, let's consider the original ratio here. In the first quadrant, sine must be positive, right? So the sine here is also positive. So the final result is cosine x. Understand? This is how we use the shortcut method to evaluate the ratio here. Okay. Any questions? Okay. Let's have a look at the second one. Okay, according to the shortcut method, first let's rewrite this in a standard form. As you can see here, this is 55, right? 55 is an odd number, so we change the name of the ratio to the cofunction. Cofunction of cosine is sine, right? And this is actually sine x. And remember that you need to determine the sign in front of the sine x here. And this sign here is determined by considering which quadrant this angle is in, right? So x plus half pi times 55 is actually x plus 52 pi over 2 plus another 3 pi over 2, right? So note here, 52 pi over 2 is actually 26 pi, right? 26 pi is actually 2 pi times 13. This means x plus 3 pi over 2 has the same terminal side with the angle here. So we only need to consider which quadrant this angle is in, right? Suppose x is in the first quadrant. That means, suppose x is acute angle. So 3 pi over 2 is here, right? This is 3 pi over 2. And plus x, x is acute angle. So plus x, the new angle must be in the fourth quadrant, right? If it's in the fourth quadrant, the original ratio in the fourth is cosine. Cosine in the fourth quadrant is positive, right? So the sign here is positive. So in this way, we know that the original expression equals sine x. Understand? Okay, so now let's consider the third question. Again, let's rewrite this in a standard form, which can be rewritten as x plus half pi times 30, right? So note here 30 is an even number. So for even number, we don't change the name, right? So equals something tangent x, right? And then we need to decide the sign here, whether it's positive or negative. Then we need to consider which quadrant this angle is in. Suppose x is acute. So note that x plus 15x is actually x plus pi plus 14x, right? And 14x is actually 2 pi times 7, which means this angle should have the same terminal side with x plus pi, right? So we only need to consider x plus pi. Suppose x is acute. So this is pi, right? This is pi. And if we add x, which is acute angle, to the pi, the new angle should be in the third quadrant, right? In the third quadrant, the original ratio tangent is positive. So the sign here is also positive. And then in this way, we know that the original expression actually equals tangent x. Understand? Okay. You can also check the solutions in this lecture slides after today's class. Okay. All right. So let's see part 3 of this course. Use equivalent trigonometric expressions to solve problems. Okay, first let's see an example here. Given that sine fifth of pi is approximately 0.5878, use equivalent trigonometric expressions to evaluate the following to false decimal places. All right, I'll give you 3 minutes to think about it. All right, any thoughts? Okay, so note that 1/5 of pi is actually 2 pi over 10, right? And 3 pi over 10 plus 2 pi over 10 is actually 5 pi over 10, which is 1/2 of pi, right? So we can rewrite the expression here with cosine 1/2 of pi minus 1/5 of pi, right? The difference between these two numbers is exactly 3/10 of pi, right? Okay, so according to the cofunction identity, cosine 1/2 of pi minus alpha equals sine alpha, which is pi over 5. And then this is actually approximately 0.5878, right? Okay, so second question. So note that 7 pi over 10 minus 2 pi over 10 here is actually 5 pi over 10, which is 1/2 of pi, right? So we can rewrite this using pi over 2 plus 1/5 of pi. And according to the property that we have proved, cosine 1/2 of pi plus alpha equals minus sine alpha, right? You can also use the shortcut method because here you have 1/2 of pi times 1, right? 1 is an odd number. So first of all, cosine becomes sine, right? And next, you need to change to determine the symbol here. In order to determine the symbol, imagine this angle is acute angle. So this is your 1/2 of pi, and plus an acute angle. The new angle should be lie in the second quadrant, right? In the second quadrant, cosine is minus, so we need to put a minus sign here. So original expression equals minus sine 1/5 of pi, which is minus 0.5878. Okay, all right, let's see another question here. I'll give you 3 minutes to solve this question, okay? All right, any thoughts? Okay, we want to evaluate secant 3 pi over 14, right? And note that here we have an angle that is 4 pi over 14, right? And note here the sum of these two angles is exactly 1/2 of pi, right? So secant 3/14 of pi equals secant 1/2 of pi minus 2 pi over 7 here, right? Okay, then according to the cofunction property, secant 1/2 of pi minus something equals cosecant the angle here, right? And we have already know that cosecant 2 pi over 7 is about 1.2790. So we can just put the number here. All right. Okay. Any questions? No? All right. So let's make summary of what we have learned today. So after today's lesson, now you should be able to first understand and prove trigonometric identities featuring minus pi, right? For example, sine minus pi equals minus sine, the sine minus theta equals minus sine theta, right? And cosine minus theta equals cosine theta, right? And tangent minus theta equals minus tangent theta. This is the first set of properties we have learned, right? So here I only list the primary ratios, and the second ratios can be inferred by using the reciprocal property, okay? Next, understand and prove trigonometric identities featuring theta plus 1/2 pi times k, okay? And you can use the shortcut method to evaluate the expression. For example, you have a trigonometric ratio 1, and then you have a positive or negative theta, and then plus 2 pi times k, right? And this can be rewritten as some trigonometric ratios here, and then theta. And then you also need to determine the signs in front of the new trigonometric ratios, right? And the trigonometric ratio name here is determined by considering the value of k, right? If k is an odd number, this new ratio is a cofunction of trigonometric ratio 1, right? And if k is an even number, the new ratio is the same with the original one, right? And the signs here, the sign here is determined by assuming theta here is acute angle and considering which angle, which quadrant this angle is in, and use the cast rule to determine the sign of this trigonometric ratio in that quadrant. And that sign is exactly the sign with the sign here. Understand? Do check the shortcut method of the class by yourself, okay? This is very useful. And next, use equivalent trigonometric expressions to solve problems, such as the problems we have practiced here and here, okay? All right, so this is all we have learned so far in today's lesson, okay? The rest of the time is reserved for you to complete and submit today's homework. You can now download the homework, complete it, and submit it before the deadline, okay? All right, class dismissed. I'll see you next lesson. Bye.